Okay, so welcome to the first post-coffee talk. The talk is given by Ian Goldberg. It's about privacy-preserving presence protocols.
Thanks, Ruben. Hi, I'm Ian Goldberg. This is joint work with Nikita Borisov, who's in the room somewhere, and George Dinezis, who was here earlier in the week but is not here today. So there's DP5 privacy-preserving presence protocols. Kenny, in his talk yesterday, mentioned Phil Rogaway's recent paper, and I couldn't resist putting up a movie poster-style pull quote from Rogaway saying, "A beautiful job at the nexus of systems, privacy, and cryptography," is how he referred to this work. Yeah, pretty sexy, eh? Nice. All right, so what are we talking about? Social applications, right? Many of you use them, obviously. There's some obvious ones like Twitter and Facebook, and also ones that are more about kind of just chatting on instant messaging, things like the older AOL Instant Messenger, AIM, and kind of the standard XMPP. Now, all of these social applications have a few things in common. The notion of accounts, right? You have an account with these things, and a notion of friends, right? So this friend notion is slightly different between the different systems. Some of them, like in Facebook, the friend notion is symmetric. If Alice is a friend of Bob, then Bob is automatically a friend of Alice. And in some, like Twitter, it's asymmetric. So Alice can follow Bob on Twitter without Bob also following Alice, right? Everything I'm going to say here works in either scenario, so it's all good, all right? So all of these schemes have the notion of accounts and of friends, and one of the features that social applications have, which is very useful for users, is a notion of presence, okay? So you want to know when your friends are online, okay? So when you log in, you want some kind of indication like this of which of your friends are online. So here we see that some of them are marked in green, and these are the ones that are online now. Some of them are either idle or away or not online. And then there are these little messages that you can put. So we call this the auxiliary information, right? So this might be human-readable messages, like away from my desk, or it might be kind of machine-readable information, such as your current IP address and port to contact you on directly, or an ephemeral public key in the case of an encrypted messaging service, or something like that, right? So this is what we call the auxiliary information. So presence allows Alice to learn which of her friends are online, and of the ones who are online, it also provides this machine-readable and or human-readable auxiliary information. So that's what we're talking about here. So how does this typically work? How does this notion, this mechanism of presence typically work? So let's take XMPP as an example. So you have an XMPP server over here, and the XMPP server knows what's called the friend graph. Okay? So this is basically every dot here represents a person, and every line between two dots represents that those two people are friends. Okay? And this can be represented in any way at the XMPP server. This in particular is the friends graph of a US high school on Facebook, but you get the picture, as it were. So the server knows the friends graph, and then let's say Bob here is online, and his friend Alice comes online. Alice authenticates to the XMPP server, typically using a username and password, but you could, of course, do more clever things. And the XMPP server says, oh, it's Alice, looks up in the friends graph who Alice's friends are, looks in its list of who's currently online, takes the intersection, and sends back to Alice, oh, yes, your friends Bob and Charlie and Dave and whoever else are online, and here's their auxiliary information as well. Okay? Then, when Alice wants to send Bob a message, Alice typically will send the message to the XMPP server. Just tell the XMPP server, please tell Bob, hi Bob. And then the XMPP server sends a message to Bob saying, Alice said, hi, Bob. Okay, so that's how these things typically work. So, what is the privacy problem here we're trying to solve? Okay, well, there's the obvious privacy problem that the XMPP server sees all of this communication traffic, right? The XMPP server sees that Alice said hi, Bob, to Bob. This is not the problem we're trying to solve today. This is a older problem and one that is already pretty well solved by end-to-end encryption, right? Things like our own OTR or TextSecure with axolotl and all of those great systems, right? So that's not the problem we're trying to solve. What is the problem we're trying to solve? So the problem we're trying to solve is simply that the XMPP server knows the friends graph in the first place. Okay? Why is the friends graph sensitive information? Okay? Well, Claudia actually touched on it in her talk, that knowing this metadata of who is friends with whom is sensitive. Knowing that your friends are all communists makes you more likely to be a communist, right? Knowing they're all hackers makes you more likely to be a hacker. There are studies that show that just by looking at your friends on Facebook, you can determine things like your political leanings and your sexual orientation. Okay? So this notion of who is friends with whom is very sensitive. And this is what we want to protect, and not just for the benefit of Alice and Bob, right? As much as protecting this information is of benefit to Alice and Bob, it's also, perhaps surprisingly, of benefit to the server itself. Okay? So many of these servers that provide these social application services to their clients themselves do not want to know the private information of their clients. Why don't they want to know this? Because if they know it, people might come asking for it. And that might be in a polite way or it might be in a not so polite way. And they want to avoid the situation entirely where somebody comes asking for this private information. Now, do people, adversaries, governments really go to businesses and try to get private information about their customers? Yes, of course. We've seen LavaBit, for example. And are buddy lists and address books, these set lists of friends, really a target of actual government concern? Again, yes. We've seen, there's the word Snowden right there. So we've seen from the Snowden leaks that the NSA actively collects address books from online traffic on the internet. So this information, this metadata, is actually very sensitive and actively being targeted. Okay? So metadata, again, as Claudia said, has some nice properties for the people who are collecting it. One is that it's typically easier to get than content data. And second, it's easier to use because it's typically machine readable and not just free-form English text or audio or something like that you would have to run through some natural language thing. Right? The metadata is really easy to use, and because of this, governments use it a lot, and Chris stole the thunder here when he said it in his talk. We kill people based on metadata, from Michael Hayden. You can watch the video to see him say that if you want. Okay? So let me introduce our system. Our system is called DP5. DP5 stands for the Dogstool Privacy Preserving Presence Protocol P. The extra P is for extra privacy. So DP5, this is our system to allow Alice to learn which of her friends are online without revealing to any server who her friends are. All right? So how does it work? So this is kind of the high-level idea. So we're going to say Alice and Bob are friends. We're going to say every pair of friends shares a symmetric key. How did they get this symmetric key? Honestly, I don't care. There are 100 ways to get this symmetric key. Either when Alice joined the network, she exchanged symmetric keys with her friends, or they have public keys and they do Diffie-Hellman, or whatever. I don't care. There are tons of ways to do this. We're going to just say at the start of the protocol, Alice has a shared symmetric key, a different one with each of her friends. Fine. So when Bob comes online, he uploads to the server his auxiliary information, things like his IP address, port, ephemeral public key, and so on, to the server, of course, encrypted with this key. So he actually uploads one record for each of his friends because they're encrypted with different keys. Okay? Then, when Alice comes online, she's going to ask the server, do you have a record for Bob? Do you have a record for Charlie? And at this point, you should be squinting your eyes at me and saying, wait a minute. And if you're not squinting your eyes at me and saying, wait a minute, you should be thinking about why you should be squinting your eyes at me and saying, wait a minute. But I'll get back to that in just a minute. So hold that squint. Okay? So Alice asks the server, do you have a record from Bob? Do you have a record from Charlie? And the server says, oh, why, yes, here's a record from Bob along with the auxiliary info. Of course, again, this is all encrypted, right? So the server can't see what it gave Alice, okay? Now, naively, you might think, well, we're good then. But again, hold that thought. So Alice has retrieved this presence record from the server. And now when Alice wants to communicate with Bob, she just communicates directly. The server is not involved, using the auxiliary information, which has both contact information, an IP address and port, for example, and an ephemeral public key to make this nice forward secret communication. So this would, of course, be encrypted. When I put encrypted text on the slide, it tends to break things with control characters and stuff like that. So just pretend this is encrypted. Fine. Okay, so let's go back to the squinty eye, right? The squinty eye is, of course, this step, right? Even though all the records on this server are encrypted, if Alice just says, oh, please fetch me the record Bob uploaded, well, then clearly the server knows that Alice is friends with Bob. Even if Alice just says, please fetch me record identifier blah for some random blah, then the server knows, well, I know that Bob uploaded record blah, and so I can correlate that Alice is friends with Bob, right? So that's also not good enough. So how do we do this? So this query here has to be a private query. Alice has to be able to ask the server for a particular record without revealing to the server what record she asked for. Okay? And this, of course, seems impossible. Who thinks it's impossible? Great. We'll get to that in just a minute. Okay? So this is, in fact, a known technique called private information retrieval. So private information retrieval, or PIR, is a known technique for downloading information from a database without revealing to the database what information you asked for. So let's talk a bit about PIR and how it works. So let's say we have a database of some kind. Let's say it's a database of patents. Okay, you don't have to imagine very hard. These databases really exist, right? And you can just look up patents on them. Fine. Alice here is a researcher. Alice wants to download a particular patent. Patent number 6368227, method of swinging on a swing. This is a real US patent covering pulling the chains of a swing sideways so that you swing side to side instead of forwards and backwards. Okay? 6368227, Google it yourself. As I said, it was a real US patent that was issued, later rescinded on the grounds of stupidity. But it was issued. Okay, so Alice is a swing researcher, and she wants to download this patent, but she doesn't want the server to know that this is the patent she was looking for. Note what I'm protecting here. I'm protecting the query. I'm not protecting Alice's identity. The sensitive information is that swings are a hot new research area, not that Alice in particular is a swing researcher. Okay? Now, this is, of course, a silly example with swings, but replace swing by 2,5-dimethyl blah blah butyrol, right? Some big pharmaceutical thing. And then you can see that if someone suddenly looks up this particular chemical, that particular chemical might be important. Okay? And that's exactly the kind of thing that the drug companies would not want to reveal to a server. Okay? So the idea of PIR is that Alice can query the server with PIR to get the database record back, and the server has no idea what she asked for. So the first question is this possible at all? Well, here's a simple example to see that it's possible. Okay? Alice connects to the server and says, please send me all the patents. And the server says, here you go. And then Alice looks up the patent she wants herself. Okay? Clearly, this is private. That has revealed no information about what patent Alice was asking for to the server. Clearly, it is also ridiculous. Right? So, the goal of PIR is to use clever math, even not so clever math. I'll show you an example in a minute that just uses high school math to download information privately from the server, just as privately as in that silly example, while transmitting less information than the whole database. Way less. Okay? And the fact is we can do this. And there are a couple of ways to do this. One is called computational PIR, in which Alice basically encrypts her query, sends the encrypted query to the server. The server can magically process that encrypted query, where magically means using things involving the word homomorphic encryption, but not fully homomorphic, the crazy kind, just the older, normal, partially homomorphic encryption, the normal kind, right, that we actually can do in a reasonable way, right? And then sends the encrypted result back to Alice, who decrypts it, okay? That's not the kind, so DP5 could use that, but it turns out it's about 100 times more computationally expensive to do that than to do it this other way. So this other way is called information theoretic PIR, or IT-PIR. And in IT-PIR, what you do is you replace this computational assumption that the server can't break this homomorphic encryption or whatever. You replace it with an information theoretic assumption that's common in privacy-enhancing technologies, which is not everyone is colluding against you. Okay? If everyone is colluding against you, you lose, just like you lose on Tor and just like you lose on e-voting schemes and stuff like that. Okay? But as long as not everyone's colluding against you, you can do this. So you have a number of different servers, at least some of whom are not evil, and Alice sends a request to each server and gets a reply back from each server and then combines the replies to get the database entry she wanted. Okay, so that's how IT-PIR works. Let's give a simple example. Okay, again, here's PIR using nothing but high school math for most values of high school. Turns out it depends where you went. Who did matrices in high school? Yeah, okay. So high school math for those of you who did matrices in high school. Okay? Fair enough. All right, so here's an example database. A database we're going to represent as a matrix where the first record of the database is the first row, the second record of the database is the second row, and so on. Okay, this is a very simple database. We'll get back to that a little later. All right, and Alice wants to retrieve one of the records of the database without revealing which record it is. Okay? We're going to use two facts from high school math to make this work. The first fact is that if you have this elementary basis vector, which is all zeros with a 1 in the ith place, and you multiply that vector by this matrix, what do you get? Oh, now who remembers how to do high school math? Okay, so you take the thing and you go, and what it does is it picks out the ith row of the matrix, right? Which is row I, which is the ith record or the ith block in the database. Okay? All right, so what we could do is just send, instead of saying give me record 3, you construct this vector here and you send it to the server and it does this product and sends you the result. But of course that's not any more private. The server can just see you asked for 001, 00000 and say, aha, the 1 is in place 3, you're asking for record 3. Right? So that's no good. So this is the second fact from high school math you need to know, which is the distributive law. Okay? And you probably learned distributive law before high school, but the fact that distributive law works on vectors and matrices maybe you learned in high school. Right? So what do? So from these two lines, you can probably predict how this very simple PIR scheme that was invented in 1995, this is the very first PIR scheme by Chor et al., 20 years ago, how it works. You just pick, say they're L servers, you pick L random bit vectors such that they add up to EI. All right? And you send the first vector to server 1, the second to server 2, the Lth to server L. Each server multiplies their vector by the database and sends you back the results. You add up the results, which is this. By the distributive law, that equals this. By the way you chose VIs, the sum equals this. And then EI times D is block I. And you're done. Okay? So again, this is a very simplistic version of PIR just to show you it is possible. Okay? Note the amount of computation you're doing is each server is doing is a vector times the whole database. Right? So the computational cost scales with the size of the database, but the communication cost, it turns out in this one, scales with the square root of the size of the database, which is much, much smaller. Okay? All right. So there are some issues with this 20-year-old scheme. For example, there's a robustness issue. What does that mean? If any of these servers is down or gives you the wrong answer, then you can't reconstruct the record you wanted. And worse, if one of them gives you the wrong answer, you can't even tell which one was cheating. Okay? So this actually was addressed about 10 years ago. There are better schemes than this that can handle bad servers. Okay? Another issue addressed in previous work is variable size records. This is a very simplistic database. It just has a bunch of records all of the same size. Right? Real databases don't look like that. It turns out previous work, you can handle variable size records as well, but it turns out we don't need that for DP5. So we're not going to use that fact. I'm just telling you that PIR can handle things better than this. And the third thing is this very simplistic query type, right? So in this very simple PIR query, the only thing you can ask for is give me block 6368227 of the database, which is great if you know the index of the record you're looking for, but that's not typically true. So previous works show how to query databases by more expressive queries like keyword-based, or even do an SQL query against the database without the database learning what the query was. Okay? It's pretty cool that you can do that. It turns out for DP5 we need something slightly different, and so we had to slightly do some invention here in PIR. So what we need to do is look up a key value pair, like in a dictionary, abstract data types, and now think back to like first year university maybe. I don't know. Whenever you learned about dictionaries, so you have key value pairs, and important, the key in here is not a cryptographic key, right? This is a key like an index into a dictionary. Unfortunately, we use the same word for this. Okay? So you have key value pairs, and I want to look up the value associated with a given key from the server without revealing what key I asked for to the server, and without the server learning what the value was or even whether or not that key exists in the database. That's important. The server can't learn whether the key is in there. So how do we do that? Okay? And what we're going to do is use that very simple PIR that I already showed you as a building block. Okay? So how do we do it? So we have our list of keys and values, and we're going to take a pseudo-random function, a PRF, which is a whisk, right? It mixes things up, right? And this PRF, this isn't exactly your kind of standard cryptographic PRF that outputs like reasonable sized values like 256 bits. This particular PRF is going to output a small number from like 1 to the number of buckets, which we'll call R, maybe 7, right? This PRF will output a number from 1 to 7, or 1 to 1,000, but this number is way smaller than your typical PRF output. But it is completely reasonable to make this PRF just by taking any standard cryptographic PRF and taking the output modulo R, right? Perfectly reasonable construction. Fine. So what do? We do what's probably obvious. You take the first key, you feed it into the PRF, and it outputs 6. And so you put key 1, value 1 in this bucket. Then you take the second key, and you put in the PRF, and it outputs the value 3. So you put key 2 and value 2 in that bucket. And so on for all the keys and values in your dictionary. Okay? And it ends up spread out like this. And because it's a PRF, they're spread out approximately equally. Right? And you can use a Chernoff bound and bound how likely it is that they're too much different. Don't worry about that. They're about the same. Okay? About number the same keys and values in each bucket. And then what you do is you picture in your mind a database matrix like the one we had before, where the first record is just the concatenation of all the entries in the first bucket. The second record is just the concatenation of all the entries in the second bucket, and so on. Okay? So now when I want to look up a particular key in this database, what do? I take the key, I put it through the PRF, and it tells me, say I want to look up key 12, it tells me that's in bucket 5. And then I just use the PIR I showed you before to request record 5 from this database without the database learning which record I requested. Right? So I download 1 record's worth of stuff, but the database does not learn which record I accessed. Okay? That's the important PIR property. Then what do? I have this record, and then I just look through it. And I just binary search it, basically, looking for the actual key I'm looking for. And if it's not there, it's not there. And if it is there, I find the associated value. But importantly, the server did not learn what bucket it was in or whether the key I was looking for was there or not. Okay? Or the value associated with the key or the value of the key. There's none of those things. Okay? Great. So, here's the straw man version of DP5. We divide time into epochs. Okay? How long these epochs are going to be very important, but I'll get back to that in a minute. So Alice comes online during some epoch, and she registers with the server for each of her friends, Bob, she takes this KAB, this is the key shared by Alice and Bob, this symmetric key I pictured earlier on, and she uses that as a key to a different PRF. This is actually a cryptographic PRF. It's not the same PRF that was used in the whisk function. Right? This is an actual cryptographic PRF with the input of the epoch number. Okay? And this PRF, it's slightly weird in that it has 2 outputs. It outputs 2 cryptographic sized things, a key K and an ID. Alice takes her auxiliary data, encrypts it with the key K using your favorite authenticated encryption function, and that produces a ciphertext C. Alice then uploads this ID, C pair as a key value pair to the database. Okay? So that's what Alice does every epoch that she's online, with every friend of hers. So this database is pretty big. Okay? Of course, it's a fresh database in every epoch. You can erase the ones from last epoch every time. But it has an entry for every friend of every user. And it turns out you kind of want to pad the number of entries, the number of uploads you do so you don't reveal how many friends you have. So it's actually even bigger than an entry for every friend for every user. Okay? Then, and we'll say why that's important in a minute, then when Bob, in the next epoch, he queries the database for the previous epoch. right? And he says, okay, epoch for T2, database for T2. What does he query? He takes this key he shares with Alice. He takes the epoch number from the previous epoch. It will output the same key and ID because pseudorandom functions are deterministic in that way. If you know the key and the input, it's the same answer. And then takes the ID and uses PIR to query the database. And what will come out, if Alice was online, then some ciphertext will come out. And if Alice wasn't online, then nothing will come out. Okay? But importantly, again, the database doesn't learn which is the case. Okay? And if the ciphertext comes out, Bob obviously decrypts the ciphertext using the key K to get the auxiliary data. Okay? So I said this is the straw man version. In an ideal world, this would just work, and we'd be done. The problem is that PIR, as I said, is somewhat expensive, and its cost scales linearly in the size of the database. Okay? And you can think about, there's good reasons why PIR needs to scale computationally in the size of the database, but not communication. Communication's much smaller. Okay? All right. So the problem is that if these epochs are too short, then you're doing this expensive computation pretty frequently. And that could be too much computational cost for you. So you might say, okay, we'll alleviate that by making the epochs longer. But if the epochs are longer, note that Bob only sees that Alice was online in this epoch in the next epoch. And so there's this latency between when Alice comes online and when Bob sees that she's online. So we can't make that an hour. That's no good. Right? So at most, that can be like a minute or two, probably, at most. Right? But not an hour. Okay? So, how do we solve this problem? Well, some of you may be familiar with David Wheeler. And David Wheeler famously said, any problem in computer science can be solved with another layer of indirection. Less commonly known is his very next sentence when he said that, which is, but that will usually create another problem. So we're going to go with this part and use another layer of indirection and just kind of wing it on the other problem. See what happens. Okay? So we're going to add a layer of indirection and make 2 timescales and 2 databases. So we have the long-term epochs, capital T's, and the short-term epochs, lowercase t's. So the capital T's, here they're pictured as being like 3 short-term, but in reality they're much longer. The short-term epochs are going to be like that minute or so, minute or 2, and the long-term epochs are going to be like a day. Okay? So that's the real scale we're talking about here. Then what happens? Alice comes online in some epoch, and what she does, I've marked in red the changes from the previous protocol. So what have I changed? Instead of using the short-term epoch number, I use the long-term epoch number here. So capital T1 in this case. And instead of Alice's auxiliary data, she uses a presence key. She makes 1 presence key, or 1 for that epoch, long-term epoch, and uses that. But importantly, whereas this is a different one for every friend, this is the same for all her friends. Okay? And that's the trick we're going to use. So basically, Alice uploads to the long-term database, the long-term epoch database, an encryption of her current presence key. All right? Then when Bob comes along, he can just use the protocol we saw before to retrieve this long-term presence key. And so can all of Alice's other friends retrieve the same presence key. Then, any time during this epoch, long-term epoch, capital T2, if Alice comes online here, say during little t4, Alice does the same protocol as before, returning to the auxiliary data here, but now, and returning to little ti here, but now instead of having a different key for each one of her friends, she just uses her single presence key. Okay? And that way she only has to upload 1 of these, not 1 per friend. So into the long-term database, she has to upload 1 per friend, but in the short-term database, she uploads 1. So this short-term database is much smaller, so the PIR is more efficient, so it is reasonable to do it every minute or two, to do PIRs every minute or two by all the users who are online, right? Whereas the long-term database, you only have to do it once a day. So how do we choose the day? It turns out the length of this epoch controls how quickly can Alice revoke someone as a friend. Okay? So if Alice says, Bob's no longer my friend, he's no longer allowed to see when I'm online, then that will only take effect at the beginning of the next long-term epoch. So we think a day is okay for that. Okay? But a day is definitely not okay for the when does Bob see that Alice has come online, obviously. Right? Okay. And then Bob retrieves in the obvious way. All right? So, implementation. We have code. Right? The PIR part, we use the per C++ PIR library, which is written in C++. The DP5 code core is also in C++, because evil language. Evil language, but another rant for another time. Networking is the cherry pipe framework in Python. And if you want to get it with Git, if you like Git, you can clone the Gits. If you don't like Git, find a friend who likes Git and have them clone it for you and give you a tarball or something. So we have a Git for both the PIR library and for DP5 itself. So we have the code for the DP5 protocol on the client side and on the server side. What we're missing right now is the glue between the DP5 client side and an XMPP client or whatever messaging client you have, right? So we need like an XMPP expert, and I'm staring at Nathan. Maybe he can help. He'll talk later. To help us glue this together into an actual client, right? Okay. So, takeaways. Metadata in social communication is being actively targeted. PIR allows you to look up information from a database without revealing what information you were looking for, even to the database itself. And DP5 uses PIR to achieve private presence, the ability for someone to look up whether their friends are online without revealing, even to the social network itself, who their friends are. Thank you very much.
Thank you, Ian. So are there questions? There's a microphone for questions.
Come on, do math in the morning. Oh, there's Nathan.
Ian, so this is work to prevent the servers who have like a central contact list for you from being, targeted
right.
and to collect. But you're still, as your client, if it's like a peer-to-peer connection, you still have to make that connection to the friend when you find out that they're online, that you want to talk to them.
Right.
So someone observing you is still going to see who your friends are.
Right. So someone observing you, if you take no other protections, will learn who your friends are when you talk to them. If you take no other protections, right? But then that's a separate problem solved in a separate way, and you can use things like Tor, you can use Ricochet, which also uses Tor, whatever. Or you can communicate using, there was a recent paper from Pets last year, Vuvuzela, or something like that, right? So those communications privacy mechanisms are complementary to this kind of private presence mechanism.
Thanks.
Hi. Yeah, we're definitely excited to implement this, and we've been looking at ways to reduce metadata leakage anyway with presence. I'm just wondering, could you use this alone to build a Twitter-like status network?
Absolutely. So DP5 basically is a short message private delivery service, right? And the short messages it's delivering in this application are presence indications along with the auxiliary info. But if you just want to privately send a message to a particular friend, you can use this but basically every person is polling every friend of theirs every epoch, right? So it has somewhat high overhead, but it does hide the metadata of communications if you use it in that way.
And then what does it look like to deploy this sort of at scale or federated or across multiple
Okay, so
geographic
federated is actually a little tricky for technical reasons. Deploying it at scale, it turns out I have a graph. Graph, click. There we go. All right, so deploying it at scale, bonus slides. So deploying it at scale, Facebook can't deploy this, okay? The costs are too high. But RiseUp can deploy this, okay? And so here we have a graph of number of users and monthly per user cost. And the per user cost scales with the number of users. And that's because the PIR database gets bigger and it's more expensive to do. So this cost is basically a combination of bandwidth and CPU. The bandwidth is pretty low no matter what because the bandwidth scales low. See, this is a logarithmic scale. But the CPU cost is non-trivial, right? So if you have thousands of users, right, the monthly per user cost is less than a penny. No problem, right? If you have 100,000 users, it's still only a few pennies. But if you have 1 million users, it's suddenly like 50, 60 cents per user, right? So not so good because that's like hundreds of thousands of dollars a month. But on the other hand, maybe if you have 1 million users and you can charge them $1 a month for a private presence service, then you can pay for this and have some tidy sum left over to pay for something else, right? But we don't actually recommend doing this for 1 million users, but anything in this range is totally reasonable. Jake.
I really like this as an idea for replacing jabberccc.de's buddy list, for example.
Exactly.
Which is a good idea. But if we look at systems like Signal, we see a totally... Well, actually, Signal's not a good example. If we look at a system like Pond, or we look at a system like a telephone, like an old telephone, where you have an address book and there's no concept of presence, I wonder if you might compare and contrast why we would want to do something like DP5 rather than just keeping our address books on our devices, which include cryptographic keys, and maybe we have a peer-to-peer connection. Like Ricochet, for example, you have a whole bunch of keys on your local machine, and there is no centralized server, and there is no centralized path. There's no single place that you route through to talk with people. And the idea of presence exists in Ricochet. It doesn't exist in, say, something like Signal because it's asynchronous. But in both cases, the buddy list is your address book, like a smart address book. And I wonder if that can solve the scaling problem in some way. And then you might use something like DP5 for federation connections being up, which would then scale for all the possible nodes in a federation.
Right. Okay. So even in DP5, it is the case that your contact list is your local address book. Your contact list is not stored on any server.
But you need a DP5 server.
You need a DP5 server only to do the presence. If you don't want presence, you don't need DP5. You don't need any of this, right? DP5 is only to provide the presence indication that users like, right? Users like to be able to see, oh, my friend, Jake's not my friend. No, Jake's my friend. Oh, Jake's online.
What the fuck, Ian?
I made him leave. But it takes a day to unfriend you, so we'll make up by then.
Okay, let's thank our friend Ian again.
Okay.